Let us now examine the relationship between weak acids and bases and their conjugates more closely. So for a weak acid that partially dissociates the protons and its conjugate base, in this example we have acetic acid, we see that the Ka, or the acid dissociation constant, is going to be equal to the concentration of the products divided by the reactant. And for acetic acid, this is 1.75 times 10 to the minus 5. For the conjugate base of acetic acid, which is the acetate ion, we see its dissociation looks like this. It produces hydroxide ions when dissociated in water. So the base dissociation constant, again, would be, you can find it by the products, concentration of the products divided by the reactant. So Kb would be concentration of acetic acid multiplied by the concentration of hydroxide ions divided by the concentration of the base. The Ka for acetic acid is 1.75 times 10 to the minus 5, and the Kb for acetate ion would be 5.71 times 10 to the minus 10. Now, since your acetic acid is a weak acid and its conjugate base is weak, then we can think of the equilibria as looking like this. Your HA, your weak acid plus water gives A minus plus hydronium ion concentration. And similar to what we did on the left, we see the acid dissociation is expressed there. And for the weak base, we can also express its base dissociation constant as HA, concentration of HA times the concentration of hydroxide ions divided by the concentration of the base. Now, let's look a little closely. For a weak acid and its conjugate base pair, for a weak acid conjugate base pair, the acid dissociation constant multiplied by the base dissociation constant should be equal to the concentration of hydronium ions times the concentration of hydroxide ions, which should give us Kw, right? And if you remember, this is the dissociation constant of water, right? So what this means, so let's look at the Ka for acetic acid. It would look like this. Acetate ion concentration times hydronium ion concentration divided by the concentration of acetic acid. If we multiply that by the base dissociation constant for acetate ion, we see its concentration of acetic acid multiplied by hydroxide ion concentration divided by acetate ion concentration. When we multiply, what do we notice can happen? The terms in the numerator and denominator can cancel, leaving us with Ka times Kb being equal to hydronium ion concentration times hydroxide ion concentration, which we know to be Kw. Right? So the K of your weak acid and the Kb of its conjugate base should give Kw. And what should this equal? 1 times 10 to the minus 14. So check it for yourself. Look at the Ka for acetic acid and the Kb of its conjugate base and see what you find. So this relationship applies to weak bases as well. A weak base, all right, we're going to write it as BOH, and its weak conjugate acid B plus would behave similarly to give the equilibria that we are going to show. So your weak base, when it dissociates in water, will give its conjugate acid and hydroxide ions, and the base dissociation constant is going to be equal to the concentrations of the conjugate acid and hydroxide multiplied by the concentration of hydroxide ions divided by the concentration of the base. For the conjugate acid of your weak base, its acid dissociation constant is going to look like this. Okay? When we multiply the base dissociation constant of your weak base by the acid dissociation constant of its conjugate acid, it should equal concentration of hydroxide ions multiplied by the concentration of hydronium ions, and this should equal Kw. Let us use this to help us in determining the pH of aqueous solutions of acids and bases. So we know that pH is equal to minus log of hydronium ion concentration, and the pH for your aqueous solution of your acid or base will depend on whether it's a strong or weak acid or base, and specifically for your weak acids and weak bases, this will depend on the magnitude of their acid or base dissociation constant. So some reminders: pH is equal to minus log of hydronium ion concentration, and pOH is equal to minus log of hydroxide ion concentration, and pH plus pOH of your aqueous solution should equal 14. So let us examine two examples. What is the pH of a 0.002 molar nitric acid solution? Now, HNO3 is a strong monoprotic acid, and it completely dissociates. So it means that the hydronium ion concentration is going to be equal to the concentration of the acid. So to find the pH, we can do minus log of that concentration. Let's look at another example. What is the pH of 0.002 molar hypochlorous acid solution? Now, HOCl is a weak monoprotic acid, and it only partially dissociates. So we must first consider its Ka, which is written here as 2.8 times 10 to the minus 8, to help determine what concentration of hydronium ions are actually produced in solution, followed by the determination of the pH. So this is showing the dissociation of HOCl in water. It produces the hypochlorite ions plus hydronium ions. The Ka expression then can be written as the products over the reactant, similar to what we've seen before. Now, keeping in mind that for every molecule, so even though HOCl is a weak acid, every time a molecule dissociates, it actually produces one of each ion. So one of each. So it means that upon dissociation of this weak acid, the concentration of its conjugate base will be equal to the concentration of hydronium ions produced. So we can rewrite the Ka expression as hydronium ion concentration squared divided by the concentration of our acid. If we input the values for the Ka and the value that we had for the concentration, we are better able to determine the actual concentration of hydronium ions that were produced. We can solve for hydronium ion concentration and then use this concentration that is determined to solve for the pH. Now, just a couple things to keep in mind. One, when we have greater than, say, 5% dissociation of the weak acid, it is better determined using the quadratic equation. So review that. And also want to mention that when we think about this example with a weak acid, similarly, it can apply to a weak base. But for a weak base, instead of considering the acid dissociation constant, we'll be considering the base dissociation constant. Okay? So let's look at acid-base indicators. So your acid-base indicator is a weak organic acid or base whose undissociated form differs in color from its conjugate base or conjugate acid form. So as an example here, we're going to write it as H indicator. When it dissociates in water, it produces the conjugate base form and hydronium ions. So when we have higher concentrations of the acid form, we get the acid color, and higher concentrations of the base form will result in the base color. So we can also write an acid dissociation, we can also show the acid dissociation constant for our indicator, which would be concentration of the conjugate base multiplied by hydronium ion concentration divided by the concentration of your acid. And we will see that the hydronium ion concentration is going to be related to the Ka and the concentrations of the indicator and its conjugate base. Now, the human eye, so remember these are indicators, they typically show us a color change. So the human eye can distinguish between these two colored forms when one is present in a concentration that's about 10 times the other, right? Keep in mind that the position of this equilibrium that we're looking at here is going to be dependent on the hydronium ion concentration of the solution. So higher concentrations of acid will result in production of more of the acid form, showing more acid color, right? And if that is lower, we're going to have increased base color in a basic solution. So therefore, when the indicator, so the acid form is greater than 10 times the base form, we'll see an acidic color of the indicator. And when we have a greater concentration of the base form, then we will see the base color, basic color. Now, keeping in mind that this derived equation that we looked at before, where hydronium ion concentration would be equal to the Ka times the concentration of the acid form divided by the base form, we see that if hydronium ion concentration is equal to 10 times Ka, meaning that we have greater acid, more acid is present, then the pH will be equal to minus log of 10 times Ka, right? If we do minus log on both sides, okay? And therefore, pH would be equal to the pKa minus 1. If we're looking at when the indicator takes base form, in this case, your base would have a higher concentration. So your hydronium ion concentration is going to be equal to 0.1 times the Ka. And the pKa, the pH, is going to be minus log of 0.1 times the Ka, which will give you a result of pKa plus 1. Therefore, what this tells us is that indicators will change color over a pH range that is close to their pKa plus or minus 1. So when we think about our neutralization titration, we know that the pH of the solution is going to be changing as the neutralization titration progresses. What we want to do is to be able to find a chemical indicator that reveals the endpoint of your reaction as closely as possible to the equivalence point of your reaction, right? So you should be able to reveal the equivalence point using a chemical indicator or an instrument response, for example, with a pH electrode. Let's look at an example of an indicator or phenolphthalein. We see going from colorless form, right, in acid, to the pink form in base. As mentioned, it is important to choose an indicator that best represents the equivalence point of your reaction. And so we'll see here that there are a number of choices, right? These are just 3 examples of acid-base indicators. Phenolphthalein, bromothymol blue, and methyl orange will have different pH ranges over which they are going to be useful for determining the endpoint of the reaction. And of course, as mentioned in the previous slide, this will depend on their pKa's. So most indicators are going to be able to show a color change over range pKa plus or minus 1. The sharpness of that endpoint determination is also going to be related to the concentration of the reagents used. So for more concentrated reagents, we'll find that there will be a sharper endpoint determination or a sharper change in pH at the endpoint.